In part A, we determine the equation of the tangent plane to the surface z equals e power x times cosine of y at the point 0, comma 0, comma 1. And so this is the formula that we utilize to determine the equation of the tangent plane. So this is given by the partial derivative of f with respect to x at the point x naught, y naught, z naught times x minus x naught plus the partial derivative of f with respect to y at the point x naught, y naught, z naught times y minus y naught plus the partial derivative of f with respect to z at the point x naught, y naught, z naught times z minus z naught equals 0. And so the first step is to write this given function as a function of x, y, z equals 0. I'm going to write down this equation as a function of x, comma y, comma z. So I write down f of x, comma y, comma z. This equals 0. That is, we can write this equation as e power x cosine of y minus z equals 0. So basically this is the function of x comma y comma z. And so we find the partial derivative of f with respect to x, with respect to y, as plus with respect to z, and evaluate at the point 0, comma 0, comma 1. So first I'm going to differentiate this partially with respect to x. So I write fx, and this equals, when we differentiate partially with respect to x, we treat the variables y and z as constant. So when we differentiate this, we treat cosine y as a constant and then differentiate only e power x. The derivative of e power x is e power x. Now this negative z, which is a constant, so it becomes 0. So we get e power x times cosine of y. This is the partial derivative of f with respect to x. Now we can evaluate this fx at the point 0, comma 0, comma 1. So we can write down this as partial derivative of f with respect to x at the point 0, comma 0, comma 1. And this equals, we have to plug in x equal to 0, y equal to 0, and z equal to 1 into this equation. So therefore this becomes, replace x by 0 and y also by 0. So it becomes e power 0 times cosine 0. E power 0 is 1 and cosine 0 is also 1. So therefore this becomes 1. So we have evaluated this partial derivative of f with respect to x at the point equals 1. Now let's find the partial derivative of f with respect to y and evaluate at the point. So I write fy, and this equals, when you partially differentiate with respect to y, we have to treat the variable x and z as constant. So when we differentiate this expression e power x times cosine y, e power x is treated as a constant, and then we have to find the derivative of only cosine y, which is negative sine y. And then if we differentiate this negative z with respect to y, here it is treated as constant, so it becomes 0. So we get this expression negative of e power x times sine y. This is partial derivative of f with respect to y. Now we will find this partial derivative at the point 0, comma 0, comma 1. So we have to plug in x equal to 0, y equal to 0, and z equal to 1 into this partial derivative. So therefore this becomes negative of e raised to the power of 0 times sine of replace y by 0. So it is a sine of 0. Sine of 0 is 0, so therefore this is going to be 0. So we determine this partial derivative of f with respect to y equals 0. Now let's find the partial derivative of f with respect to z. So we have to treat the other variables x and y as constants. So therefore we write f of z. This equals, when we differentiate this with respect to, partially with respect to z, this becomes a function of x and y. So they become entirely 0. And the derivative of negative z is negative 1. So I write down negative 1. And so therefore we can find this partial derivative at the point 0 comma 0 comma 1. And since it is independent of any variable, this is going to be 1. Sorry, it is negative 1. So we found this partial derivative of f with respect to z equals negative 1. Okay, now that we have determined the partial derivatives, we can substitute into the equation of the tangent plane. So therefore, we write equation of tangent plane is the partial derivative of f with respect to x at the point 0 comma 0 comma 1 times x minus x naught is 0 plus the partial derivative of f with respect to y at the point 0 comma 0 comma 1 times y minus y naught is 0 plus the partial derivative of f with respect to z at the point 0 comma 0 comma 1 times z minus z naught is 1. So I put 1 here, and this equals 0. So let's substitute the partial derivatives into this equation. Replace fx 0 comma 0 comma 1 by 1. So this becomes 1 times of x minus 0 is x plus the partial derivative of f with respect to y is 0. So therefore this becomes 0 times of y plus the partial derivative of f with respect to z is negative 1. So I put negative 1 times of z minus 1, and this equals 0. We see that 0 times y is 0, and this is 1 times x is x. So we have x, and this is negative of z minus 1. So if we distribute the negative, we get x minus z plus 1, and this equals 0. We can rewrite this equation by adding z on both sides. So therefore we get z equals x plus 1. And so this is the equation of the tangent plane to the surface at the given point. Let's do part B. Here we determine the equation of normal line to the surface at the point. So here we utilize this equation of line, that is r of t is given by the point plus t times of the direction vector given by the partial derivatives. So let's write the equation of normal line r of t, and this equals we put the point vector, that is 0 comma 0 comma 1 plus t times of the partial derivatives at the point. So fx of 0 comma 0 comma 1 is 1, and then the partial derivative of f with respect to y at the point is 0, and then the partial derivative of f with respect to z at the point which is negative 1. So this is basically the vector equation of the normal line. We can give the parametric equation of this normal line. So it is x of t, and this equals we take this point and the direction number multiplied by t. So it is 0 plus 1 times of t, and so this gives x of t equals t. Now let's write y of t, and this equals we take this point which is 0 plus 0 times of t, and so this is basically y of t equals 0. Now let's write z of t, and this equals we write the point which is 1 plus negative 1 times of t, which is negative t. So this gives z of t equals 1 minus negative t. So these are the parametric equations of the normal line to the surface.